All right, welcome back. I'm going to show you a new type of problem. Test style question where you don't do the whole antiderivative, you do part of the process and you stop when that part of the process is done. So in this problem, we're asked to use a substitution to transform an integral into a different integral. We're told what the substitution is. So that part of the thinking process is done. I'll start the transformation process. We have antiderivative. I'm replacing the 3x squared with a w. So this x to the power of 5 is going to stay there temporarily. E to the 3x squared becomes e to the w. And we know that the dx has to be replaced by a dw term. I'm going to take the derivative of the substitution. dw by dx is 6x. Rearrange, we get dx is equal to dw divided by 6x. So dw over 6x. And then simplify. So there's a 1 over 6 in front. Now we have antiderivative of x to the power 4 times e to the w dw. And this is wrong. It's not wrong, it's just it's not ready yet. We haven't fully done what we're supposed to do. What to do about x to the power 4? X to the power 4 is a problem, but there's a way to fix it. But if w is equal to 3x squared, then x squared is equal to w over 3. Just rearrange. Well, what's x to the power 4? And x to the power 4 is equal to x squared squared, so w over 3 squared, which is w squared over 9. So I'll substitute that in up here for x to the power 4, replace it with w squared over 9 and get everything in terms of the new variable. So 1 over 6 integral w squared over 9 e to the w dw. So 1 over 54 integral w squared e to the w dw. And that's the complete transformation. We've transformed it completely in terms of the new variable. Transformed in terms of the new variable. Let's do another one. Okay, so another expression. We want to transform the antiderivative of x times the sine of x times e to the 1 over x using the substitution w is equal to 1 over x. So let's go ahead and see how this plays out. So I'm going to have x sine of x times e to the w, and then I'm going to replace the dx. So dw by dx, the derivative of 1 over x. So I'm taking the derivative of x to the power of negative 1, I'm going to get negative x to the power of negative 2. And then rearrange. dw by dx is equal to negative 1 over x squared, and then cross multiply. So dx is equal to negative x squared dw. So that'll go here, negative x squared dw. And we have a bit of a problem. We have negative integral x sine of x, actually x cubed sine of x, times e to the w dw. Mixed expression. We're not done. What we need to do is we need to use the substitution differently. If w is equal to 1 over x, we can rearrange. W is equal to 1 over x and cross multiply. So w times x is equal to 1. And that means x is equal to 1 over w. I'm going to use that everywhere. So we have minus integral 1 over w cubed times the sine of 1 over w times e to the w dw, which I'll clean up a little bit. Negative integral sine of 1 over w e to the w over w cubed. Over w cubed. And that's our transformed integral. Is it better? Is it worse? It's worse. I think it's worse. But we've transformed it. Transformed in terms of the new variable. And to continue, I'm not even sure what we would do, but hey, we've transformed it. That's all that was asked of us. All right, here's another one. Looks nasty. We have antiderivative of tan squared times secant squared times e to the tan of x. And we're going to use the substitution w is equal to tan of x to transform this thing. So I have tan squared. That's going to turn into w squared. I have secant squared. Nothing good happens there. And e to the tan of x becomes e to the w. And we know we have to get rid of that dx. Put it in terms of dw. So we'll take the derivative of our substitution and hope everything cancels. So dw by dx is equal to secant squared. That means dx is equal to dw divided by secant squared. Cross multiply and cross divide. Oh no. Having some problems. Okay, so I'll substitute that in. Antiderivative of w squared secant squared of x. Oh, gotta substitute that up here. dw over secant squared x. Forgot I wrote that. And we get the secant squareds canceling top and bottom. We just follow the instructions, use that substitution, and then we get antiderivative of w squared e to the w, and everything's done. So this one was nicer. We didn't have to go back to our substitution and use it backwards. So this is transformed as required. It's completely in terms of complete in terms of the new variable. No x remains. Okay, really nasty now. Use this substitution, w is equal to e to the x, to transform this statement into something that will not be much better, maybe even worse. But we're just going to follow instructions. So I'm going to replace all the e to the x's with w's. I get w times w plus 1 over w minus 1 to the power of x. That's going to be a problem. We have to do something about that. The dx will replace right now. So dw by dx, derivative of e to the x is e to the x. Rearrange. dx is dw over e to the x, which is dw over w. So dw over w. We get some cancellation going on, which is good. W on top, w on the bottom. But we have a problem still. We can't declare victory. We still have an x in there. W plus 1 over w minus 1. Problem with x. It's a mixed expression. A mixed expression is bad. It should be only in terms of one variable. So what do we need to do? We have to look at our substitution and use it backwards. If w is equal to e to the x, then let's take the ln of both sides. Ln of w is the ln of e to the x. We have a cancellation law. So cancel ln e. So x is equal to ln of w. And we'll substitute that in. So we have integral of w plus 1. Well, the bracket's a big bracket, so I'm going to be careful. Integral of big bracket w plus 1 over w minus 1. And instead of power x, it's power ln w. There you have it. Now it's been transformed into just the new variable. Transformed as required. It's entirely in terms of w with no x's. Is it better? No, but the first one was horrible. Like, this is just a nightmarish type of problem, nightmarish type of antiderivative. Now the last part here, this is not testable. We're not going to make you do these. It is kind of neat. How do you take the antiderivative of the secant of x? And there's a few different things you could try. You could rewrite secant as 1 over cos, let w equal cosine of x, and you won't get very far. Maybe start using some trig identities. Maybe start talking about square roots. Maybe invest into learning about something called inverse trig functions, and partial fractions, and integration by parts, and these other integration strategies that we don't know. Not yet, at least. And there is a way forward by brute force using a combination of integration methods. There's also a way forward that's elegant, that requires no brute force at all. And it's kind of a parlor trick. We're going to use that most powerful strategy in mathematics once again. We're going to, I call it the most, it's really the second most powerful. There is a more powerful method. Now, what could be more powerful than multiplying by 1? Adding 0. It's extremely powerful. You just have to add the right form of 0. You add something and add the negative of that thing. Just make sure it's the right thing. You can solve any problem that way. But multiplication by 1 is still pretty powerful. Okay, now what form of 1 are we going to use? And what speaks to you when you look at this? And whatever it is that's speaking to you is wrong, because this doesn't speak to anyone. And if it does speak to you, you have other problems. Whoever dreamt this up is a different type of genius. It wasn't me, it wasn't anyone who's alive today, but the form of 1 to use, this is amazing, is secant of x plus the tan of x divided by secant of x plus the tan of x. So at some point in history, someone saw that as like, hey, oh yeah, I'm just going to multiply by that. And then it works. So after this one like creative genius figures out the strategy, the rest of us just copy that person. We just say, yeah, good idea. Why didn't I think of that? Okay, so what I'm going to do next is I'm going to simplify the top. I'm going to expand. I have secant times secant, that's secant squared. And then I have sec x tan x divided by secant of x plus the tan of x. Now what? Like I took a nice thing, secant, replace it with a horrible thing. How is this better? But look at the bottom. What happens if I take the derivative of the bottom? Well, the derivative of secant of x is sec x tan x, and the derivative of tan of x is secant squared. So what I have here is the antiderivative of f prime over f. I have ln of f as my antiderivative. So I'll show you in steps. I'm going to let w equal the denominator. Let w equal secant of x plus the tan of x, the thing that we had for top over bottom, for the 1 is equal to same over same. dw by dx, derivative of sec x is sec x tan x, derivative of tan is secant squared. Now we'll rearrange. So dx is equal to dw divided by that stuff. And we'll plug that in for our substitution. So we have antiderivative of secant squared of x plus sec x tan x divided by w times dw over stuff. I just don't have room to write it in. And this stuff cancels with that stuff. And we end up with antiderivative of 1 over w, dw, which is ln absolute value of w plus c. I forget the plus in the last one. Oh, no, I didn't finish the last one. Never mind, we didn't. Okay, and then ln absolute value of, undo the substitution, sec x plus tan of x plus c. Marvelous. Marvelous. But how on earth did that person think to do that? I have no idea. See you next time.